Another thing we're going to do is take a look at why our regular idea of atomic orbitals, like S's and P's and D's, does not work for atoms that are involved in bonds, and why we have to make a modification called hybridization to explain that. The molecular shapes that we see are not always predicted by atomic orbitals. In fact, lots of times they aren't. An example would be H2O. If you think about oxygen and where the electrons are in the valence shell of oxygen, remember that it is helium, 2s2, 2p4. And so the valence shell electrons are in either an S shell, which is full, or in a P shell. So thinking about P shells, remember they're kind of these dumbbell-shaped things. There's going to be one in this axis, one in this axis, and then there's another one that's kind of in and out of the screen. So in the orbital notation for the P subshell, one of those orbitals is full. Let's assume that's the one that we can't see because it's coming in and out of the screen. But the other two have one electron each in there. So electron here, maybe electron here. So that means if hydrogens are going to bond and share electrons, they're going to have to share electrons in a space that's here and a space that's here. And those P subshell orbitals are 90 degrees from each other. So that would seem to suggest that oxygen should be the point of a 90-degree angle. But in fact, we know that's not true because VSEPR theory predicts that those two lone pairs are going to give us a 105-degree angle, whereas atomic orbitals predict a 90-degree angle. So that's a problem. Another problem is the sharing possibilities that we see all the time in covalent bonding are not predicted by where the electrons are that are available for bonding. An example of this is seen in CH4. If you look at carbon in its orbital notation for its valence shell, it's helium, 2s, full shell, 2p, 2. So there are 3 orbitals there. Only 2 of them have a spot for an electron to be shared. So that would suggest that you could only bond 2 hydrogens to this molecule, but we know that's not true because CH4 bonds 4 hydrogens. So these questions that were raised here led to a theory called hybrid orbital theory, which we're going to investigate now. Hybrid orbital theory is basically a statement that says when orbitals with shared electrons can overlap to the greatest extent possible, that's when bonding is the most stable. So we want the orbitals that contain the shared electrons to extend as deeply into each other as they possibly can for stability. And because atomic orbitals don't allow that, orbitals hybridize, or they change their shape to accommodate greater overlap when bonding begins to occur. The first type of hybridization is going to be sp hybridization. It's called sp hybridization because it's going to make 2 orbitals that are hybridized from an s and a p. So in BeCl2, the atomic orbital notation is 2s full and then no electrons in 2p at all. But we see from the fact that BeCl2 exists that beryllium has to have the ability to share electrons in 2 different spaces. So the hybridized model is that the S and one of the P's are going to make this other kind of orbital, and the 2 electrons that are in the 2s, they're going to each be in one of these hybridized sp orbitals, and then 2 of the 2p orbitals are going to just remain unhybridized. So looking at the atomic level, this is what an S is, remember it's spherical, would look like, and our 2p orbitals, they're those dumbbell-shaped orbitals that are all 90 degrees from each other. We're going to take this S and one of these p's, and we're going to make a different type of orbital called an sp hybrid orbital. And they are shaped like a large lobe on one side and a small lobe on the other side. So kind of like a p, except it's a lopsided p orbital. And there's two of them. They're centered on the nucleus, so the nucleus would go there and there. So these are kind of pulled apart so you can see their shape, but they would be conuclear. They would be right on the nucleus. And then we would still have two unhybridized P's that don't have any electrons in them. So that means that this electron here can be available to share with some electrons from chlorine, and this other electron would be available to share with another electron from a chlorine, and that allows us to make two bonds. Another type of hybridization that occurs is called sp2 hybridization, and the name suggests that it's going to take one s and two p orbitals hybridizing to make this possible. So in CH2O, carbon is making three bonds. If you look at the atomic orbital notation for carbon, that doesn't look possible because there are only two places where there are lone electrons that could share. So hybridization is going to take two p orbitals and the single s orbital and hybridize them to make three sp2 orbitals, and that leaves one unhybridized p orbital. And then the electrons spread out, which allows us to have three bonding sites for carbon to make this molecule. So again, looking at the shapes, here's our S's and our three P's. And here's our hybridization. We get three orbitals. They make a triangular planar arrangement with each other, and they're shaped kind of like the SPs were. There's a big lobe for bigger overlap and a small lobe, and those things are conuclear. So the nucleus is here, here, and here, and they're just kind of exploded apart. And then we still have one unhybridized 2p. If you show them all put together with the nucleus in the center, this is what it looks like. And so overlap can occur here with a hydrogen, here with another hydrogen, and here with the oxygen to make those bonds. sp3 hybridization. So you probably know the story. sp3 means it's going to take an S and three P's, and that's exactly the hybridization that takes place. We don't have any unhybridized P's. We have four sp3 hybrid orbitals, and that allows overlap in four places. So we get these four sp3 hybrid orbitals. They look just like an sp or an sp2, big lobe, small lobe, and that's where all the electrons go. Put them all together, and you can see that they all overlap, which allows bonding with an H here, 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 and here, with great overlap for strong bonds. PCl5. In order for PCl5 to form, that phosphorus has to be able to bond in 5 places. In order to do that, something called sp3d hybridization takes place. So we have only 3 possibilities for bonding, there, and there, right now. But if we take all 3 P's, the S, and one of the D's, and use them to form hybrid orbitals, we can then have 5 half-occupied orbitals where overlap could occur to make a bond. So those 5 orbitals make 5 sp3d orbitals, and that leaves 4 unhybridized Ds. So again, looking at the shapes, there's our S and our P, and there's the 1D that we're going to use. They're going to hybridize to make 5 sp3d hybrid orbitals, and that's where the bonding can occur to the chlorines. We know that octahedral molecules exist. Steric number 6 is a thing. So another type of hybridization that will allow for that is sp3d2, which just uses 2 d orbitals and then the S and all 3 P's. So this is what that hybridization would look like in terms of orbital notation. It produces 6 orbitals, sp3d2 orbitals, that are each half occupied, so that allows for overlap to bond to the 6 fluorines in this case. So in terms of orbital shapes, there's our S, our 3 P's, and now we get 2 D's involved. And the hybrid orbitals are going to look like this. Remember, they're going to have a little lobe on the other side, large lobe on the bonding side, and that's where all of the fluorines are going to overlap with to make the bonds. And then those 3 unhybridized 3D orbitals just don't contain any electrons at all. So we're going to wrap this up by talking about what orbitals do what. And there are 2 different types of bonds that occur when orbitals overlap. The first bond that happens between any 2 atoms is called a sigma bond. And many bonds just only have that one bond, that sigma bond. This is made by overlapping orbitals that are right on the axis that exists between the two atoms. That's a sigma bond. So in this example, we see sp3 hybrid orbitals from one carbon overlapping with the sp3 hybrid orbital from the other carbon, and that overlap of hybrid to hybrid, that's the sigma bond. Sometimes it's a hybrid orbital with an unhybridized orbital. So hydrogen can't really hybridize because it only has the one orbital, and so an unhybridized hydrogen is overlapping with an sp3 hybrid orbital in carbon to make that bond. And then sometimes there are hybrid orbitals and unhybridized orbitals that overlap with each other. That could also be a possibility. Any additional bonds that are made between atoms are called pi bonds. And these are made by overlapping unhybridized orbitals off axis. The bond is going to have two segments that are off the axis between the two atoms. So here's the axis between the atoms. These are going to overlap here and here, and that's going to make your bond. Something like this. In addition, any lone pairs that occur in the compound, they're going to be held in hybrid orbitals to minimize repulsion, just to get as far away as they can with each other. So in addition to overlapping as deeply as possible, hybridization allows lone pairs to get as far away from one another as possible to minimize repulsion. Example, PCl5. The phosphorus in the middle is going to be sp3 dehybridized so that there can be overlap in 5 places. Each of the chlorines is going to sp3 hybridize so that it can have 4 regions of electron density, 3 for the 3 lone pairs, and 1 to overlap with the sp3 dehybridization in the phosphorus. So here's a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. And they're all by hybrid overlap. Another one, C2H4. So in C2H4, this is what the Lewis structure is going to look like. Each carbon is going to be sp3 hybridized, and this is an sp3, and this is an sp3 from 2 different carbons. So this is one of the carbons, this is the other carbon, and that overlap makes the sigma bond. Another sp3 hybrid orbital on this carbon overlaps with an unhybridized 1s from a hydrogen, and that makes that bond. Same thing here, and here, and here. And that leaves us one unhybridized p orbital in each carbon. Those are going to overlap kind of sideways off axis, and that's what makes the second bond in that structure, and that's a pi bond. Another example is N2. In N2, nitrogen is sp hybridized. That takes an S and a P and it leaves 2 unhybridized Ps. So one unhybridized P is 90 degrees from the other here. Here's the overlap that makes the sigma bond, and then you have 2 unhybridized Ps on each of the nitrogens, and the overlap of those make the 2 pi bonds, and that ends up being the structure. C2H2. So the Lewis structure for this looks like that. So there's a triple bond, and the steric number for carbon is 2, which means we need 2 hybrid orbitals here. So this is going to sp hybridize. So the sp hybrid orbitals from the 2 carbons, remember this is a carbon, this is a carbon, that makes the sigma bond. And then the other sp hybrid orbital is going to overlap with a hydrogen's unhybridized 1s there and there to make those bonds. And then we have an unhybridized p here and here from the 2 atoms, and then each one is going to have a second unhybridized p orbital, just like in nitrogen. And those are going to overlap to make the 2 pi bonds. Okay, so I've made this little thing called valence bond theory for dummies. If you weren't following all of that and you don't want to have to think about the details of how hybridization works, most of the questions that you're going to be asked about on the AP exam are going to take this form. They're going to ask you, what is the hybridization of the blank atom in the blank molecule? So they'll show you a picture of the molecule or ask you to draw a Lewis structure, and they'll want to know what is the hybridization on different atoms in the structure. Or the other thing they might ask you is how many pi and sigma bonds are present in this molecule. So you can do that by following this strategy. First, draw the Lewis structure. Second, find the steric number for any atom that you're interested in knowing the hybridization of. Third, the steric number will match the number of hybrid orbitals used. So example, if the steric number is 2, that means you're going to need 2 hybrid orbitals. So it's S and a P hybridized. If steric number is 3, it's SP2 because you need 3 orbitals. There's only one S, so you have to use 2 Ps. If it's 4, that's SP3. If the steric number is 5, then an S and a P and a 3 only gives you 4, so you have to get a D involved, so that's SP3D. And if the steric number is 6, it's SP3D2 because you need 2 d orbitals to do your hybridization, so you can end up with 6 hybrid orbitals. Then, if you're looking at your structure, if there's a single bond and that's all it is, there's 1 sigma bond. If it's a double bond, there's a sigma bond and a single pi bond. If it's a triple bond, then it's a sigma bond and 2 pi bonds. So there's never more than 1 sigma in between the same 2 atoms, but there could be multiple pi's. Example, what's the hybridization of the N atom in NH3? So remember, here's the Lewis structure. We've done this one before. Steric number is 4. That tells you that it's sp3. How many sigma bonds are there? Well, every bond is at least a sigma bond. There are 3 bonds, so there's 3 sigma bonds. How many pi bonds? You would have to have a double or a triple to have a pi bond occur, so there aren't any. Another example. What's the hybridization of the P and the Cl atoms in PCl3? Lewis structure looks like this. Everything is got steric number 4. So all of them are sp3 hybridized because you have to have 4 hybrid orbitals. How many sigma bonds? Well, there are 3 sigma bonds because there are 3 bonds. What orbitals overlap to form them? Well, it's sp3, sp3 overlap. How many pi bonds? There aren't any because all of these are single bonds. Xenon tetrafluoride. We've done this one already. It's going to be fluorine there, there, and there. Full octets. We still don't have enough electrons. We had to end up putting 2 lone pairs in there. Okay, so steric number of xenon is 6. That means it's sp3d2 to get our 6 hybrid orbitals. How many sigma bonds? They're only single bonds, so there's 4. How many pi bonds? None, because all the bonds are single. Another example is HCN. Here's the Lewis structure. What's the hybridization of all atoms? Well, hydrogen is unhybridized. Carbon, steric number 2, that is sp hybridized. Nitrogen, also steric number 2, that is sp hybridized. How many sigma bonds are there? There are 2. There's one between carbon and hydrogen, and there's one between carbon and nitrogen. Pi bonds? There are 2 pi bonds. The second and the third bond between carbon and hydrogen are both off-axis, unhybridized orbital overlap pi bonds. This is a complicated one. It's asking for what's the hybridization of all atoms in this molecule below, and some lone pairs are missing. So let's look for places where lone pairs would be missing. Oxygen does not have a full octet. 2 electrons go there. This nitrogen does not have a full octet. Neither does this one. This oxygen needs 2 pairs. This nitrogen needs 2 pairs. That nitrogen needs 2 pairs. I think we've got that covered. Okay, what's the hybridization? We're looking at steric number. So this is going to be sp3 because there's 4 steric number. This is also going to be sp3. Steric number 3 here, so this is sp2. 3 regions of electron density here, this is sp2. This is sp3, steric number 4. Steric number 4 here, sp3. Steric number 3, this is sp2. This one also, sp2, steric number 3. This is steric number 3, sp2. This is steric number 3, sp2. Steric number 4, this is sp3. This is also steric number 4, sp3. sp2, steric number 3, also sp2, steric number 3. So I think we have that all covered. How many sigma bonds? Well, every bond is a sigma bond, so you just count every single bond. And if you do that, you're going to find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 sigma bonds. How many pi bonds? These are only the doubles or the triples. So we've got 1, 2, 3, 4 pi bonds in this structure. Very last concept. A single bond is considered to have a bond order of 1. A double bond is a bond order of 2. A triple bond is a bond order of 3. And resonance can show fractional bond orders. So if we recall, an NO3 ion look like this, but it also could be drawn two other ways, like it is in resonance with this structure where the double bond is on the left, and this structure where the double bond is on the top oxygen and the two on the sides are single bonded. So the bond order is not 1 or 2, but it's in fact 1 1/3 for this structure.